Alright, we're going to do the next section, which is all about medians and altitudes. So remember what, first we'll talk about medians. Remember what a median is? That is a line that goes to the midpoint of something else. So a median is a segment that goes from a vertex to the midpoint of the opposite side. And here's a picture of it like this. So I have some random triangle, and this line here is going to be my median line because it's cutting into these two parts which are going to be congruent. Now, with triangles, every single triangle will have a median. And it's always going to start at the vertex, it's always going to the opposite side, but it's always going to be making these things congruent. Now, we have our theorem for the concurrency point of this. The medians of a triangle are congruent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So if I drew out lines here and here, this point here is going to be my point of concurrency. That means that from here to my point of concurrency, this distance is 2/3 from here to the other side. That's what this theorem is saying. So if I have D to C is equal to 2/3 of D to J. F to C is equal to 2/3 of FH. E to C is equal to 2/3 of E to G. So this concurrent point of concurrency here is going to be 2/3 the distance of this whole length to the midpoint. The point of concurrency for medians is called the centroid, and a centroid is always going to be on the inside of a triangle. So I know there's a lot of vocabulary going on right now, and there's a lot really hard to kind of distinguish between the two. So, so far we've had perpendicular bisectors, angle bisectors, and medians. Perpendicular bisectors go with the circumcenter of the triangle. Then, and this line here is going to be perpendicular. Angle bisectors are making congruent angles, and they go with the incenter of the triangle. Then we have medians, and they go with the centroid. Now let's going to try a problem where we're given lengths of certain things, and we have to figure out the other length of it. Okay, so in this problem, in the diagram here, we're told that XA here is equal to 8, and we want to find the length of XB. Well, from our theorem from what we just got before, we know that XA from the vertex to the concurrent point is 2/3 of the full length. So I can set up XA equals 2/3 XB and then plug in what I know. So that means 8 is equal to 2/3 of XB. So then I can multiply both sides by 3/2. And I would get that 12 is equal to XB, because 3/2 times 8 would be equal to 12. So 12 is equal to XB. So for these, you just need to make sure you're plugging in the right points and putting in the right things in the right side. In this one, to follow up, if ZA is equal to 9, what is the full length of ZC? So again, I set it up that ZA is 2/3 of ZC. I plug in 9 for ZA and 2/3 times ZC. I do multiply both sides by 3/2, and this would go into 3 times 9, 27, divided by 2 is 13.5. So ZC would be 13.5. So basic algebra problems for these. Now the next thing we're going to do is, next and last one is going to be called an altitude. Now altitude is a little bit weird and tricky. So altitude is going to be going from the vertex of an angle of a triangle to a side that is perpendicular to the opposite side. And an altitude can be inside, outside, or on the side of a triangle. So just like imagine that I were to take this line here and I drew it out here and I needed to go to a line that's perpendicular. So when I hit this point, I may not be perpendicular, but if I draw another line up here, that would be my perpendicular point. Or if I go, so what I'm trying to say is that it doesn't always have to be inside the triangle, the line that you're looking for. And we'll get more into that in a bit. So we're going to do some examples where we're given some things and we have to identify whether it's a median, an altitude, or neither of them. Okay, so we're given this question: for triangle PQS, is PR, this one here, going to be a median, an altitude, or nothing? Okay, so I noticed that this line here and RS are going to be perpendicular to each other. So my PR is a segment that goes from P to SQ, the line that contains SQ. Since PR and QR are perpendicular, this will be a altitude for these two, because you're going to the side that is opposite of P. So PR is a segment that extends from vertex P to the line containing SQ. So the side opposite of P. So I'm going from here down to here. So I'm trying to find a perpendicular line from this point down to here. This is where my altitude is. PR is perpendicular to QR, so PR is an altitude of QS. Then I have another example. For PQS, is QT a median, altitude, or neither? QT goes to this point here, so it goes from the vertex to the opposite side of Q. Since PT and P and TS are going to be congruent, T is the midpoint of this line. So QT would be a median because it's going from the vertex to the midpoint here. Remember that this point here is the altitude because it's going from a vertex to a line that's perpendicular to the opposite side. And this opposite side is not inside the triangle. All right, next, let's go into different examples for acute, right, and obtuse triangles for altitudes and the name for it. Okay, concurrency of altitudes theorem. The lines that contain the altitudes of a triangle are going to be concurrent. That should be known by now. All these lines are always going to be concurrent. The point of concurrency is called the orthocenter. So far we have 4 things, 4 different kind of lines, and 4 different points of concurrency, each with a different vocab term. The orthocenter can be inside, outside, or on the triangle. For acute, going from the vertex to the lines that's perpendicular to the opposite side. So this is making right angles. So the point of concurrency is going to be inside the triangle. For right angles, it's going to be on the right angle. It's going to be at the point here. Because this line here, and that line here, all on that single point here, where the 2 smaller sides are meeting. That's where the orthocenter will be for right triangles. And then for obtuse triangles, it's way outside. So this is just way outside for this example. But notice how if I extended this line out, if it was perfectly straight, it'd come down, and then this line here is coming down this way. So remember, I have to try and extend the lines out to get the different ones. So obtuse is going to be outside. All right, we're going to do one example of these things, and then I'm going to give you a list of all the different ones that we've had before. Okay, so in this example, we're given triangle ABC. A is 1, 3, B is 2, 7, and C is 6, 3. They want to know the coordinates of the orthocenter. All right, so from here, what I need to do is I need to find some ways I can get some perpendicular lines. Now again, I have some line that's horizontal. So I know that's going to be easy to find a perpendicular line to this. So since AC is horizontal, I know that a perpendicular line must be vertical. So that means that I have a vertical line going up and down, but I just need to know where. But I know that it must go through the vertex of the opposite side. So I'm going to go from B down to A. And that would be my point there. So to find the equation of the line containing the altitude of AC, since AC is horizontal, the line containing altitude to AC must be vertical. The line has to pass through the point 2, 7. The equation of the line is x equals 2, because x is going to be 2 and 7 is going to be constantly changing. Next, I have to find another one. I'm going to choose BC. So I have to find a line that's perpendicular to BC first. So first I'm finding the perpendicular line. So I have to find that. So first I need to find the slope of BC. I can take a look by just looking at it, or I can do the equation, but I did the equation already here. The slope of BC is -1. So the line perpendicular to that is 1. And I know the line must pass through this point A, 1, 3, because A is opposite of BC. So the equation of the line is y minus 3 equals 1 times x minus 1. So y minus the 3 point slope times x minus the 1 point. And I can simplify this into y equals. Then from here, all I need to do is solve these systems of equations. So x equals 2 and y equals x plus 2. Those are my two lines that I know. So y equals 2 plus 2, y equals 4, so my orthocenter is 2, 4. I could have also done this line here, and notice that my right angle is there, and done this line here to make sure my right angle is there. And my orthocenter would be the point where these two are crossing, which is right here. 2, 4. All right, last thing we're going to do is just a summary of all these 4 different ones and what they are going to be. All right, perpendicular bisectors, they are going to have the point of concurrency called the circumcenter. Next one we had was angle bisectors, and their point of concurrency is called the incenter. The next one we had was in the beginning of this lesson today, which was medians, and their point of concurrency is called the centroid. Last but not least is altitudes, and their point of concurrency is going to be called the orthocenter. All right, so we're going to be doing a lot of problems with these in class, finding orthocenters, finding medians, and trying to figure out if we can find ways to memorize differences between these points.